Hi! In this video, we'll be talking about a really awesome type of program, and that is simulations. So what is a simulation? Well, a simulation is a type of program that simulates some real-world situation or some real-world phenomenon. So simulations mimic real-world events without the cost or danger or overhead of actually building and testing the actual phenomenon in the real world. So let's virtually test and virtually create these real-world events that we want to study, which is awesome because there's a lot of really important things that we need to build and we need to test, and sometimes we don't have the material or the resources, or it's too dangerous to actually physically make it. For example, bridges. There are several bridge building simulators that will give you a pretty good idea if your bridge design will actually hold up in the real world. If it's sturdy, if it can take the weight that it needs to take, if it can withstand the wind. We can simulate all of this and actually design a successful bridge without ever picking up a piece of wood, which is incredible. We also use simulations in education. So there's flight simulators that will actually train pilots about all the parts of a plane and what it feels like to fly and all the things you need to be paying attention to without ever stepping into a cockpit. So we use programs to simulate flight. Another example of a simulator is a gravity simulator. So this is a program that's simulating how particles interact with each other in space due to gravitational forces. So this could be very valuable for a NASA Apollo trip, something like that, to make sure that the trip you've planned out will be successful, that you're not going to crash into a planet, and that all your calculations are actually correct. You can use a simulator to test out your trip. So these are just some examples of simulators that exist. And really, one of the most important parts of any simulation is the model. So simulations are generated based on a model of how the world works. So at each moment in the simulation, it is a new generation, a new frame in time, and it's just rules dictating how the world plays out. And those rules are described in the model. So a model is really just a set of rules for how things interact inside the simulation, inside this little virtual world. Let's look at a concrete example of this. What's a good example of a model? Well, one very famous simple simulation is Conway's Game of Life. And this is just a simple simulation that simulates what cellular organisms might look like living and dying in a petri dish. So here's the model for the Game of Life. The model is we have a grid of cells, and each cell is either alive or dead. It's on or off. And to start off with, in this grid, we will have a random number of living cells just randomly distributed through the grid. And on each iteration of the simulation, at each new moment in the simulation, cells will live and die according to the following rules. We look at each cell and we count its neighbors. If a cell has fewer than 2 living neighbors, then it dies. There's not enough living cells around it to sustain itself. If a cell has exactly 2 neighbors, then it stays the same. If it was dead, it stays dead. If it was alive, then it stays alive. If a cell has exactly 3 neighbors, then it comes to life. So if there was no life there, there now is. But if it has 4 or more neighbors, it dies from overcrowding. So this is just one example model of how the Game of Life could play out. This is simple rules that dictate how these cellular organisms are living and dying in a crowded space. So this is a simple model, but if we wanted to, we could make it much more complicated and study how these populations of cells grow and shrink based on various factors. Maybe we introduce disease into the model, or we introduce genetics into the model. So maybe each cell has a random chance of being born with a given disease, and then it can infect the cells around it, and we see how that plays out. Or maybe if a certain cell has been alive for 30 generations, then its children, its offspring, are more likely to survive in future generations. So we can constantly be complicating the model to study the things that we want to study and kind of see what that simulation might look like. But there are trade-offs when we're making our models simple versus complex. So the simpler the model, generally the faster the simulation is going to be because there's less rules. The simulation can happen much faster without having to compute much, doing that many computations. As the model gets more and more complex, there's more and more rules to keep track of and more calculations to do. So it takes more computing power to just generate the simulation. So there's kind of trade-offs here. We need to decide when we want a simple versus a complex model. Usually, all models will simplify the world in order to really focus on the one important thing that you really need to be simulated. So for example, in the Conway's Game of Life, this simulation, it's ignoring disease, it's ignoring gravity. Gravity has no effect on these cells living in this dish. Really only dealing with 2 dimensions instead of 3. We're not dealing with, how deep into the petri dish they are versus the surface. It's just a very simple grid of cells living and dying based on neighbors. But maybe if we wanted to simulate gravity or we wanted to simulate disease, we would introduce that into the model. It would just make it more complex. So it really depends on what you're trying to study. And we see this a lot of times when we're developing programs. The intended purpose of the program will affect how we develop it, how complicated we make it versus how simple we make it. So let's look at one more example of a complex versus simple simulation. Let's take gravity, for example. So in that first example we showed of gravity simulator, this is a pretty complex model of gravity. How this is working is that at each moment in the simulation, every single particle in the simulation is getting pulled towards every other particle by a force that is calculated using this equation. The force is equal to some gravitational constant times the mass of the first particle times the mass of the second particle divided by the distance between them squared. And it does that for every single particle in the simulation, for every single pair of particles. So that's a lot of computation to do to calculate how these particles are getting pulled around. And maybe that's what you need. Maybe you need that level of precision. But maybe you don't, because a much simpler model for gravity could be just there's a single ball and it's going to get pulled towards the ground. So this is a very simple model of gravity. We're going to say instead of all these particles, there's just one, and it has an x velocity and a y velocity, an x speed and a y speed. And for every moment in the simulation, we're going to move it based on the velocity and then just add 5 to y. Just add 5 to the positive y direction. And the idea here is that with each passing moment, gravity is pulling this ball down towards the Earth. So it's increasing the y velocity. And of course, if you hit a wall, you reverse the velocity so that it bounces away. And we see that this gives us a pretty realistic simulation of gravity. The ball's bouncing around. And maybe if we're making a video game or we're just making a video or we want to have this effect, this is a good enough simulation for our purposes. But if we're NASA and we need to make sure that our astronauts are going to make it around the moon and come home safely, we're probably going to use the more complicated simulation and then just have a much more powerful computer doing the calculations. So that's something to keep in mind, the simple versus complex model that the simulation runs on. So why do we make simulations? Well, we've seen that we can use them to kind of test our ideas before putting them into reality. We can use them for education. We can make these flight simulators that teach people how to fly. Simulations can also be used to predict things about the world. We can create a model and then use real information about the current world and put that in the model and then simulate the future thousands of times to find out what's most likely to happen in the future. And let's look at a concrete example of this. So there's a website, 538, that uses simulation to make a lot of predictions about sports, about politics, and they're very accurate. So the way this works is this is an example of them predicting the current election, Clinton versus Trump. So what they do is they take the polling data from each state and they say, okay, here's the current, general polls in the country. And then they factor into the model, okay, well, here's the demographic of this state. Here's the general voter turnout of this state. They put in some uncertainty, so they factor in uncertainty. And then they just simulate the future up until the end of the election thousands of times. And they say, who's going to win each state? And on average, patterns show up. So we can say, we simulated this election thousands of times, and usually Trump won Texas and Clinton won California, things like this. And using this technique, they're able to really accurately predict the future, predict things about the world using these simulations. Same thing with sports. They can look at all the data for the current players, say who's injured, who's having a really good season, who's having a really bad season, and just simulate thousands of seasons to get an idea for who the best teams are. So here we see that the Cubs, on the average simulated season, they had a record of 104 and 58, so they've been doing really well. That means they have an over 99% chance of making the playoffs. So the simulation is really powerful for predicting things about the future. What's incredible is we can also use the same technique of just simulating the same thing time and time again to actually train computers to do new things. For example, we can give it a model of how chess works. We can say this is how this chess game works. These are all the possible moves you can do. These are the rules. And just play yourself thousands of times, thousands of simulations. And over time, patterns start to emerge. You can say, oh, generally this move leads to a win and this move leads to a loss. And after thousands of simulations, the computer gets better at playing chess, which is incredible. This is such an incredible use of simulations. So simulations are really cool. What are some of the benefits? Well, simulations allow us to form and test our hypotheses about how the world works. Gravity, that's just a theory, that's just a hypothesis. And we can make the simulation and say, okay, yeah, that looks right. Let's try this and, constantly improve our hypothesis. We can test and improve the hypothesis easily without actually having to make a physical experiment. And we can constantly improve the simulation with rapid testing. If we run the simulation thousands of times, we can recognize the problems with it and improve the simulation. So that's a crash course introduction to simulations. It's a wide field of programs, a very widely used type of program. Let's see some simulations in action.